two quadratic forms of discriminant 20. These quadratic forms are x squared plus 5y squared and 2x squared plus 2xy plus 3y squared. How do we decide if a prime number is represented by some of these forms? Well, it is represented by at least one of them, if and only if 5 minus 5 is a quadratic residue, right? So P is represented by one of them, if and only if minus 20 over P is equal to plus 1, which is the same as P congruent to 1, 3, sorry, maybe not 3, 1, 3, 7, or 9 modulo 20. This is a direct computation, once again, kind of obvious one. So, how do we decide? Suppose we are given some prime number that is congruent to either 1, 3, 7, or 9 modulo 20. How do we decide which of these forms represent P? Any ideas? So, you see, suppose that P is congruent to 3 modulo 20. Then you can easily check that it cannot be represented as x squared plus 5y squared. Why is it so? This is because it is not a square modulo 20. The only invertible squares modulo 20 are 1 and 9. And any number of the form x squared plus 5y squared must be a square modulo 20. If P is congruent to 3, then it is not a square modulo 20. And so it cannot be represented by x squared plus 5y squared. If y is even, it is easy. If y is odd, then you can replace x by 5 minus x, as far as I remember. No, 5 minus x will work. Or not? Yeah, 5 minus x, of course, will work. Yeah. Correct? So,
exactly like for each number modulo 20, we have only one polynomial which represents.
one what?
Do we have primes which are represented by both polynomials?
No.
And
I will explain why. So this is an idea behind genus theory. Genus theory is a theory that will allow you to differentiate a bit between these forms. So these forms actually lie in different genera. Let me explain. So let me formulate an easy lemma that will clear things a little bit. So this is an idea by Lagrange. He observed that to decide whether P is represented by one of these forms, you need to consider P modulo 20 and nothing else. Lemma 1. Let D be congruent to 0 or 1 modulo 4. Okay, let D be a fundamental discriminant even. Chi sub D be the corresponding character. And then f of x be a quadratic form of discriminant d. Suppose we have all this data. First of all, values of the principal form that is, what is a principal form in this case? Principal form is the form corresponding to the principal ideal. What is this? Can you tell me? Principal form is either x squared minus d over 4 y squared or x squared plus xy plus 1 minus d over 4. Okay? Y squared. So one of this is a principal form. The other is not even in integral of binary quadratic form. So values of principal form form a subgroup H inside the kernel of HD, KD, sorry. So there is a subgroup inside the kernel that is generated by values of principal form. And second, values of F are coset of kernel of KD by H. Sorry, I said something strange. Sorry. A coset of H in kernel of KD, okay? Класс смертности они образуют.
Сейчас мы, значит,
Sorry, in Z over dz star, we only work modulo D, okay? Let's work modulo D, like in the previous case.
Сейчас мы вот по классу как форму получаем?
По классу? Ну, это интересный вопрос. Что там? Мы берем какой-нибудь идеал, берем его как эту самую, берем его как решетку, смотрим, что за квадратичная форма получилась на этой решетке, еще там поделить нужно на какой-то из детерминантов. В общем, там такое рассуждение. Okay? You can try to figure out this, but I will work with classes of quadratic forms, not classes of ideals. Okay. Now, the first statement is obvious. This is because set of values of the principal form are, of course, closed under multiplication, right? Product of principal ideals is still principal. So these are closed under multiplication, so they form a subgroup necessarily. Any subsemigroup is a subgroup. Okay. Now we need to prove that values of F form coset. This is an observation by Gauss. If F is primitive, means that the greatest common divisor of coefficients is 1. And M is an integer, a non-zero integer. Then there are integers x and y such that f of xy is equal to m and capital M are coprime. So for any integer, there is a value of our quadratic form that is coprime to a given integer. Okay? How do you prove such a result? Any ideas? Primitive means that greatest common divisor of all coefficients is equal to 1. There is no common integer factor of your quadratic form. Okay?
The claim is that small m exists.
Small m exists. There is a small m that is represented by f and also coprime to capital M. How to prove such a result? What?
F has infinite value.
Infinite number of values. So what? You see, to prove this result, let us first prove it when m is a prime number. Okay?
When m, actually we can take small m to be
not exactly this. Suppose that f of xy is equal to ax squared plus bxy plus cy squared, then f10, f01, f11, one of them is coprime to p, where p is any prime number, right? Because it's a, c, and a plus b plus c. If they are both, say all three divisible by p, then a and b and c is divisible by p, and you have a non-primitive form. Right? Okay. Then if m is equal to p1 to the alpha 1 and so on, pk to the alpha k, proceed by Chinese remainder theorem. Okay? So you can choose your pair to be congruent to what you need using Chinese remainder theorem. Okay, so this is a funny observation. How do we use this? Well, let us only prove the fact about coset when D is an even discriminant. Okay, so suppose that D is equal to minus 4n, n is odd square free. What can we do then? Then there is an m such that f of xy is equal to m coprime to n, right? First of all, to 4n even. And then I claim that you can transform your form to have m as a coefficient at x squared. How do you do this? Any ideas? This form, f, is actually equivalent to some form which has m x squared as a first summand, I claim. So you can choose x, y to be coprime, right? If they are not coprime, then you can cancel out the factor, and you still get the desired m. Okay, so m still will be coprime to 4n. So you can.
What we want equivalent form such that.
Equivalent form that starts with mx squared. I claim that you can do it. Assume that x and y are coprime. Find say, z and t such that xz minus yt is equal to 1, they are coprime, then you can consider f of, oh, this is bad, whatever, x, capital X, plus, sorry for that, plus t capital Y. Next, you get y capital X plus z capital Y. This form in capital X and capital Y is clearly equivalent to our form, right? Right? But it is also equal to a x plus and so on squared plus b xx plus and so on yx plus and so on plus c yx plus and so on squared. If you compute a coefficient at capital X, you get ax squared bxy cy squared. This is equal to m. Okay? So you can assume that that your form starts with a number coprime to 4n. Okay? So f of xy is equal to mx squared plus bxy plus cy squared. Now let's multiply it by m. mfxy is equal to m squared x squared plus mbxy plus mcy squared. This is equal to what? This is equal to mx plus some b prime y squared plus ny squared. So you can find such a b prime that I mean this is equivalent modulo d. Okay, this is a completion to the square. So this means that for any form, you can choose a single integer such that m multiplied by your form is represented by a principal form. This, of course, concludes the statement that this is indeed a coset, right? A coset, coset of values represented by your principal form. Okay?
And because m does not depend on...
M does not depend on xy. It only depends on the form. Oh, I have a little time left, but I hope you are not too bored with me, so you can listen for like 10 minutes more. So, okay. What can we get now? For any quadratic form, we get some coset by h, right? Let's call this coset a genus of your form. And to any form, any form lies in some genus. We say that form lies in a genus if it has this fixed coset. Okay? Now, suppose that you have only one class in every genus. What? No?
So every class has some genus.
No. Every genus consists of several classes. Okay? If forms are equivalent, they represent the same residues modulo D. And if they are not, they still can represent the same residues. Then we call them these forms of the same genus. Okay? So there is a class, and there is a larger thing called genus. Okay, so suppose you have one class per every genus. Then, of course, the representability of your prime numbers is completely determined by residues modulo D. This would be nice. One could say this would be convenient. So the numbers D with one genus per class are called convenient numbers or idonial numbers. If every genus has one class, the number D is called convenient. I do not really, I'm not sure at my spelling of what convenient. Convenient, okay. So, what can we say about convenient numbers? I can actually show that there are only finitely many convenient numbers. How does one prove this? Well, if we have only one class per genus, what?
Sorry, and is it true that every genus has equal number of?
Of course. This is because you see, every genus is a coset of principal genus in the class group, correct? Principal genus is genus containing principal form. Due to the fact that you can multiply forms using composition law, you